3, 2, 1.
Okay, welcome to the last GADEPS talk. Actually, the next week is the interview, so it's not a talk, so we can say it the last talk. So today, Haluk Sengun is going to talk about Bianchi modular form.
All right. Thank you very much. Thank you, Hussein, for the invitation. It's a pleasure to be here, meet your group at IMPA. And I hear that it's the last talk, so it's I guess it's a pleasure, but not in the sense that it's finishing, and pleasure is a significant slot. Yes. Right. Okay. So I'm going to talk about so-called Bianchi modular forms. These are kind of very natural generalizations of classical modular forms, which are quite dear to my heart. And as looking at the group members of at your group, so I going to make this quite expository as a gentle introduction. Depending on your interest, we can delve into different directions as we go along. But I'm going to try to talk about some basic aspects and maybe some connections with motives which might go, might be closer to your taste in your group there. And periods. Originally, I wanted to talk more about maybe the some of the periods, especially mod P versions, but I realized that it might go too much into Selma groups and Galois representations, which might be away from the general interests of the group. So I'll try to deviate a little bit of from what I said in the abstract. But anyway, so the idea is we're gonna have some some really laid back, informal, friendly chat about these so-called Bianchi modular forms. Okay, so I promised that I'm gonna make an icebreaker. So this my last name. So this is Turkish. Shen means happy or glad or nice. Yeah, and Shen and Gün is day. So it's happy day. So that's my last name. And Haluk means someone who gets along well with others, kind of a nice guy as a meaning. Its roots are in Arabic, but I think it's quite Turkified, and they don't really, in Arabic language, they don't use it as a name. That's what we do. Right. Okay. So let's look at the setup. Please do let me know if you can't read or if it's too small. So I'm going to basically, the idea is we move away from SL to Z, the classical modular forms. We generalize it by enlarging the ring from the integers to a ring like Gaussian integer. So what I'm going to do is I'm going to replace the rational numbers by a quadratic imaginary number field. So here D is a positive square-free integer. This is my shorthand writing of square-free. I saw it years ago somewhere. It stuck with me. It's not very smart, but yeah. So this is because it's negative D, so it only has a pair of complex embeddings. You can go into the reals from this number field, so it's totally complex and degree 2. So it's imaginary quadratic, as people say. And I'm going to use the so-called Bordeaux notation Z sub k to denote the ring of integers of this number field. And of course, this is a very simple description. It's either generated by this root minus d or 1 plus root minus d over 2. So it says rank 2 Z module. And what we want to do is we're going to consider groups of the form. Well, I guess you want to first start perhaps with SL2, where you replace Z with ZK. But it's since we are inside the actually complex number, so I'm going to actually just simply go with GL2, and a slight modification will kill the center, so we're going to look at PGL2. So I'm going to, in other words, look at PGL2 ZK. So this is my so-called, what I'm going to call this a Bianchi modular form. And why Bianchi? a Bianchi group. Sorry, I apologize. I'm ahead of myself. Bianchi group. So this is a Bianchi group, and so it's basically named after Luigi Bianchi. He was a well-known, I guess, geometer at the time, based in Pisa, I believe, in the 1880s. So he started very systematic study of these groups through their action, which I'm going to get into in a minute. And as early as 1892, this is, of course, influenced by Klein's study of the classical modular group, which was in 1880s. This is Bianchi's systematic work was actually predated by what's that guy? Picard. Picard studied the case of the so-called Picard group. Sometimes this is called Picard group with Gaussian integers. So Picard studied this specific group in a more limited way earlier, but Bianchi did a very systematic study. So these are named after Bianchi, these groups. And of course, the idea is we want to, kind of go beyond the classical modular group by not enlarging the size of matrices, not in that direction, but you enlarge the size of the ring where the entries of the 2x2 matrices come from. Okay, so of course, the idea, going back to Klein, is that we study these groups, these are discrete groups, through their action on suitable spaces. Right, so what's that suitable space? As in the classical modular group acts on upper half plane. So here we have the upper part of R3. So this is, in other words, hyperbolic 3 space. So this group, the Bianchi groups, act on hyperbolic 3 space. So a natural model of, I'm going to use this curly h sub 3. Maybe the 3 is not necessary because there won't be any other h around. But so this, what you can do is you can simply take the upper part of R3. So complex numbers. Maybe I'll so you got the horizontal directions, but in the third height direction, you only take positive height. So yeah, so if visually speaking, so you have so like the complex plane, I guess xy, and then you only go up r plus, and this is the complex plane with xy directions, the usual. So a typical element q will look like the horizontal coordinates. I identify the horizontal plane with complex numbers and height, positive height. And of course, as a space, this is the space, but of course we take the hyperbolic metric on this so that it's the usual Euclidean distance inverse proportional to the height. So you take dx squared plus dy squared plus dr squared. That's the Euclidean distance, but you as in the upper half plane with the hyperbolic plane, distance is inverse proportional to your height, which means that, of course, going up in the positive height direction is, of course, going to infinity, but also going towards r equals 0 to the bottom C plane is also going towards infinity. So that the boundary of hyperbolic 3 space in this upper half space model is simply that copy of complex numbers with height 0 together with the point at infinity, which you can, of course, see as the projective line over the complex numbers. Right, and in this as you can see, the geometries, all your intuitions from upper half plane work here. So this is just a 3-dimensional version of hyperbolic plane, which is actually quite convenient. So the geodesics are half circles perpendicular to the bottom plane, and or half circles with infinite radius, so vertical lines going up to infinity. So these are the usual geodesics, the same as in 2-dimensional situation. And right, and so yeah, so the isometries, orientation preserving isometries of hyperbolic 3 space can be identified with PGL2C, which of course is the same as PSL2C because complex numbers are algebraically closed. But if you want to describe now, of course, you want to say, okay, Bianchi groups, how do they act here? Well, if you really describe the action in terms of these coordinates, it becomes quite messy, which is a kind of a little turn off at first. But there is a okay, why is I thought I was gonna see page 2 here. Okay, so this is page 2. Now I'm gonna come down here, add a new page. But we can do the following. So there's an elegant way of describing the action so that the action looks just like the action of classical modular group on upper half plane, just like a fractional linear transformation. So to do that, you basically take your hyperbolic 3 space and embed it in Hamiltonians. I don't know how familiar you are with, so it is the usual Hamiltonian quaternion algebra generated by these 4 guys with the usual I squared minus 1, j squared minus 1, k squared minus 1, and k equals I times j. But you can actually go even one more step and split the Hamiltonian algebra embedded into 2 by 2 complex matrices. That becomes even more simple. So what you can do is if you have your point in the hyperbolic 3 space with z horizontal coordinate, complex number, and r the height, assign it to the 2 by 2 complex matrix r minus r z bar. Remember, r is real right now, so in general you would have a bar here as well. So that if you have a, of course, in particular, this is an embedding of complex numbers as well, because like this from the first coordinate, if you have a z in general, complex number can be viewed here as a 2 by 2 matrix in this format. And then you let me call this embedding phi. So the action then is if you have an ABCD. Here I'm doing the a little bit abusive with my notation. So if I have my so elements of this because I quotient out by the center, these are equivalent class of matrices, but it's really harmless. It's really so I'll just use matrix notation. So if you have ABCD in your Bianchi group and you want to act on a Q like this, so you just do almost like a fractional linear transformation. So you just do phi A times phi Q plus phi B. So this is a 2 by 2 matrix. Remember, all these are 2 by 2 matrices. And then you don't want to division would be a little bit meaningless because matrices are not commutative. So what you do is instead of writing a denominator, so I want to put the inverse on the right. So phi C, phi Q plus phi D inverse. So it can be checked that this is an invertible. The second 2 by 2 matrix is invertible. So you put it on the right-hand side. So this is the action. You can unfold this and get a very kind of a tedious description in terms of these 2 coordinates. You can find it in literature a lot of places. But anyway, so this is the action. And this action is properly discontinuous. Properly discontinuous. I mean, this actually works for any element in PJL2C. This works. Then you would, maybe I should put here just in case. So yeah, to be more real. Anyway, so this is properly discontinuous action, which means if you take hyperbolic 3 space and quotient out by gamma, let's say gamma is a finite index subgroup of my Bianchi group. Think of it like a Hecke subgroup, like gamma naught of n or something. That's the kind of most classical type of finite index subgroups that we want to think about. So if you look at these quotients, because the action is properly discontinuous, so these will be nice hyperbolic 3-folds. If your group has finite order elements, you might have some orbifold singularities, but otherwise, if it's torsion-free, if your gamma is torsion-free, then this will be nice, smooth hyperbolic 3 manifolds. They will not be compact. because of my parabolic type of elements which fix points at infinity. So they will have cusps, not compact. They have cusps. Yeah, there you go, one more line. But they have finite volume. So this is very similar to the situation. This is our analog of the modular curve, upper half plane quotient out by gamma, where you get a hyperbolic twofold. We now get a hyperbolic threefold. And these threefolds, hyperbolic threefolds, are actually, of course, some of the basic features of these threefolds reflect the arithmetic of the underlying number field. For example, if you look at if you use the full Bianchi group, PGL to ZK, and look at the quotient by, sort of say, level 1 modular Bianchi modular curve. It's not a curve or anything, so I'll get to that. But anyways, if you look at this quotient, so this has number of cusps, for example, is equal to class number of the underlying number field. This kind of stuff you might be also familiar from Hilbert modular forms. And this is quite general phenomenon. And also, if you look at the volume of these this hyperbolic threefold, the volume will will involve the Dedekind zeta function of the number field. So there is a relationship between the arithmetic of the number field, underlying number field, and some of the geometric features of this threefolds that we obtain. But most striking features, maybe for a long time, maybe kept these Bianchi groups as exotic compared to Hilbert modular groups, is that because this is three-dimensional real manifold, it doesn't have even a complex structure. So you cannot even begin to think, oh, is this the maybe complex points of an algebraic variety or something? That doesn't even make sense, because these guys don't even have complex structure to begin with. So no visible link or visible immediate link to algebraic geometry, which means a lot of the beautiful connections and tools coming from algebraic geometry when you study things like, I don't know, SL2Z or SP symplectic groups, they don't exist here, or Shimura varieties in general. And this has implications. I guess as an interesting digression, I mean, people have, I guess, even from the 70s, experts started thinking about these. If you go beyond, for example, Hilbert modular varieties, like this guy here, you lose connection to algebraic geometry, and this becomes kind of puzzling, especially, I guess, in the 70s, when people started all these cool things about Shimura varieties. Suddenly, you step to imaginary quadratic extensions, you lose all that beautiful connections. But of course, there was perhaps the idea that maybe these kind of manifolds are they are real locus of some algebraic varieties, and that idea was, I guess, people tried it, but I think they gave up quickly. But one notable remark is that because I understand that moduli spaces are quite of interest to your group there. You could actually see this kind of Bianchi threefold sitting inside as the real locus. Maybe I'll write it like this, of a Siegel threefold, suitable Siegel threefold. I'll say gamma dash for a suitable level structure acting on Siegel genus 2 plane, Siegel upper half plane, Siegel upper half plane, plane of genus 2. So as you well know, so this kind of quotient of the Siegel-Apprat plane of genus 2, these are coarse moduli space of abelian surfaces, and this threefold, real threefold, is going into this complex three manifold embedded, and it sits inside the real locus as the real locus. Maybe a couple of copies, not just maybe gamma itself, but you might need a couple of groups very related to gamma to get the whole disconnected components of the locus. But so there is perhaps an interpretation here that this is going back to Goreski, Mark Goreski and Yan Tai. In the 2000s, they looked at this example. So this gives this embedding gives gamma to my threefold, hyperbolic threefold, a moduli interpretation of very strange type of abelian surfaces. They call abelian surfaces with anti-holomorphic multiplication by the my ring of integers zk, or maybe an order in that, depending on gamma, I guess. So as far as I know, this didn't really go anywhere. It's like a very exotic, curious type of construction observation. But yeah, I guess if you really want to strictly say that there is a modular interpretation, which is quite strange and hasn't really been of use. But I wanted to mention that. So okay, so these this is the basic of the kind of what's the situation with the this is the situation with the modular quotient arithmetic manifold that you get from these Bianchi groups. This is my number 4. Please interject if you have any questions anytime. Now, maybe let me move on to what are the analogs of classical modular forms. I'm going to just stick to weight 2 to make the discussion as simple, but already at weight 2, there's more interesting stuff going on, so to say, compared to higher weight. Yes, please.
My mouse started to work. Anyway, I think it might be possible to write down the map before taking the quotient, no? From H3, this calligraphic H3.
Yes, of course. Yes. Yes.
Some explicit.
Yes. In fact, there is an embedding of SL2C or I'm working with PGL2C here, but it's like that was a little technical minor variation. So you go into SP4C, and this embedding will depend on your fixed K. You do an embedding with your K in mind, and that will, of course, then take your Bianchi group into the SP4Z, and the geometrically there will be a geometric embedding of your hyperbolic free space into the H2, and this will be equivalent with respect to the embedding of the groups and so on. Yes, that's how it works.
And at the end of the day, this Bianchi modular form must be restriction of Siegel modular forms from this door, or even it's not different.
Of course, there are ideas of so if you take a Siegel modular form and restrict it to this embedding of hyperbolic free space that sits inside the genus 2 Siegel plane, you're bound to get some automorphic objects, automorphic forms of certain types, but there is the maximal compacts, they match up U2 SU2. So that makes this kind of this embedding kind of nice in the sense that the maximal compacts, they give you the so-called weights of the modular forms. So in this sense, it's a nice object. So when you restrict the automorphic form on SP4 to this hyperbolic free space thing, you do get a meaningful automorphic form in the sense of SL2C. But of course, it could be. These kind of restriction maps are usually not terribly good. For example, Hecke actions are usually not preserved. You can do this kind of restriction even at SL2C, because SL2R sits inside SL2C and upper half plane sits inside hyperbolic 3 plane, hyperbolic 3 space. So you can think of actually even restrictions of Bianchi modular forms, which I'm about to talk about, to restriction to upper half plane. These kind of restrictions are well studied. I guess people have thought about this for a long time. But as I said, the Hecke action is not preserved under such restriction maps. That makes it not terribly nice. But there are certainly some results you could try to express the restriction as certain sums of eigenforms and things like that. But you won't in general surject onto the whole space of Bianchi modular forms by this kind of restrictions. But there is, I think Böhrer might have some actually work of maybe he mentioned to me years ago. Adrianov actually did this kind of stuff. For different purposes, but yeah, so this kind of thing can be done. You take a Siegel modular form restricted to hyperbolic 3 space, and then integrate it against the Bianchi Eisenstein form, things like that people have done. Right, so let's talk about Bianchi modular forms. So what are the kind of modular forms associated to this kind of modular group? So these are, now, if you're familiar, you can try to keep an analogy with the Hilbert modular real quadratic situation. So you could take the real quadratic extension of Q, or maybe as I'm doing right now, you can take an imaginary quadratic extension. But the flavors are very different. For here, the modular group is SL2R times SL2R, acting on 2 copies of upper half plane. Whereas, so you get a basically 2-dimensional complex manifold or 4-dimensional real manifold, whereas I have a 3-dimensional real manifold acting on hyperbolic 3 space. So this product space is not hyperbolic, so it is a more complicated geometry, whereas hyperbolic 3 space, the geometry is very similar to upper half plane in terms of it's very similar. But then again, this is a Shimura variety. This has a nice moduli space, interpretation where this guy has no complex structure. So there are pros and cons. But anyway, so Bianchi modular forms. What are these objects? I'm only going to talk about weight 2 guys. Those are kind of the nicest to talk about, and in some sense they have more interesting features compared to higher weight guys. So a Bianchi modular form of weight 2, this is the only kind of weight I'm going to talk about, of some level structure gamma. Let's say gamma, you'd fix a some finite congruent subgroup, is a real analytic function. Remember, I don't have a complex structure, so there is no holomorphicity or anything to talk about. So it's going to be a function. It's going to be vector valued, function on hyperbolic 3 space, valued in 3-dimensional complex. So 3-dimensional complex vector space C3. And such that, of course, we have first a transformation property under the action of gamma, my level group gamma. And that transformation property looks like this. If you have, maybe I should use small f. It's much easier. Small f from the modular form. If you have gamma acting on an input f gamma q is symmetric square of automorphic factor j gamma q inverse acting on fq for all q in hyperbolic 3 space and gamma in my level group gamma, where, so what's this automorphic factor? It's actually more or less, I defined it earlier in this guy. So if you have your gamma ABCD, given by ABCD, and if you have your Q point in the hyperbolic free space, the automorphic factor is kind of that denominator I mentioned earlier. This guy here. So in other words, yeah, CZ plus D basically in the classical language, classical version. So you do phi C, phi Q plus phi D. So remember, this is a 2x2 matrix. It's actually invertible. So you take that 2x2 matrix, the automorphic factor. Well, you take the inverse of it, but yeah, so you take that guy, and you take the symmetric square of that 2x2 guy. That gives you a 3x3 guy. And then this is a 3-dimensional vector, so you act on it. So this is the transformation property. And the point is that why aren't we having a complex valued, scalar valued guy here? Sitting inside SL2C. I see that I'm switching back and forth between GL, SL, and PGL and stuff, but it's cosmetic. Anyways, the maximal compact is SU2, and remember in the classical case is SL2R, and the maximal compact is SO2, but SO2 is abelian, so it has all one-dimensional characters. So that's why you always have scalar valued. Classical modular forms are scalar valued, whereas this guy has a unique irreducible representation of dimension n for each n, and these are the symmetric power representations. So the weights are given by these symmetric power representations. So I'm essentially looking at weight 2. That's the symmetric square representation. So we get these. Our Bianchi modular forms are necessarily vector valued guys, transforming under this symmetric power representations. So that's the transformation property, and then the other guys, other properties are more or less similar. So you want F to have kind of slow growth towards infinity. I'll leave it vague on purpose, towards infinity, towards cusps. At most polynomial growth, and of course you want kind of an analyticity property of we don't have holomorphicity anymore. We don't have a complex structure, so the best you can ask is for harmonicity. So F is harmonic. Right, and you can also add, we say F is cuspidal if it vanishes at cusps. So you can either express this as vanishing of certain Fourier coefficients. These guys also have Fourier expansions because they are periodic under, well, depending on your group, but I'll be working with gamma naught of n type of guys. So you'll have these upper triangular guys. So because of this translation invariance, they will have Fourier expansion, Fourier Bessel expansions, a little bit more complicated versions of Fourier expansions of classical modular forms. And you can interpret cuspidality as vanishing of certain coefficients, constant terms, or vanishing of certain integrals, which is more or less the same thing. But yeah, so we can just think of it as it vanishes as you go to infinity, very fast decay. Right, so these guys, so all functions of this type, they form a vector space, a complex vector space of finite dimension. This follows from very general results of Harishchandra. So if you have an arithmetic group, some kind of transformation property forms that are gamma invariant under some transformation property have control growth, and they are killed by certain differential operators. They call it a Z finiteness property. Z here is the is the universal enveloping algebra of the center of the universal enveloping algebra, things like Laplacians and stuff, then necessarily that space of functions has to be finite dimensional. But a very fundamental issue of Bianchi modular forms is that I guess you don't have dimension formulas for these spaces. One of the most fundamental questions: do we have dimension formulas for these spaces? No, we don't. Let me move it here. There are no dimension formulas.
So Haluk, the gross condition is necessary, because, for example, in the case of Siegel modular forms, because of the codimension issue, you don't need it. But in this case, you have zero-dimensional cusp inside three-dimensional object. I was thinking maybe one can remove it, or it's not possible.
The growth condition, this one, you're saying?
Yeah, exactly.
Yeah, so we do need it. I don't think you can remove this. Are you thinking of...
No, I mean, is there any example that they do not satisfy the gross condition?
Yes, you can cook up functions like, yeah, I mean, I never studied those things, but yeah, there are functions violating the second one. You can still have the other ones, but not the second one. Okay. So you're saying that you don't need this for in the Siegel case.
Yeah, exactly.
Is that your motivation?
Well, for the classical upper half plane, you need it because you have zero-dimensional in one-dimension complex dimension. Mm-hmm. But from Siegel modular form, starting from genus 2, you don't need basically the gross condition.
Is that some kind of Köhler principle, or no? That's not.
No, this has to do with extension. No, I mean codimension bigger than 2 subvarieties of a variety. If you have function outside, they automatically extend to the.
I see.
That's the codimension 2 loci.
Yeah, as far as I know, I don't think this works here. Thank you. That's an interesting point. Now, the dimension formula business, I won't delve too much into, but it's one of the very exotic situations of Bianchi modular forms. There are several ways to approach this. For example, in the classical situation, which also works in general for Shimura varieties, at least in principle, you can interpret these type of modular forms as sections of certain line bundles. You can use things like Riemann-Roch to get at least in principle a formula that you can compute with. Of course, I mean, in practice, that formula might be very complicated to execute, but still you have a formula for example, Hilbert modular forms. So, but because we don't have any connection with algebraic geometry, there are no Riemann-Roch type standard approaches possible that we can employ. That doesn't work. Another important tool to get dimension formulas that works for classical modular forms or Hilbert modular forms is that you can use trace formula methods. Trace formula. But the trace formula methods, that they don't work here. It doesn't help because if you're familiar with the automorphic representation theory, so the infinity type of the automorphic representations here, they're principal series representations. They're not discrete series. So they are not isolated in the spectrum. So the trace formula cannot pick up those principal series that correspond to these Bianchi modular forms. And so, yeah, so we don't have any formulas. And you see very strange behavior, actually. If you look at, for example, take a prime ideal, P prime ideal. So this is really like taking gamma naught of P in the classical situation. I take a prime ideal and look at my levels group, Hecke congruence subgroup gamma naught of P. And I look at weight 2 cuspidal modular forms. And so let's say P is split in the sense that P is not inert. So it splits this prime ideal with prime norm. So I'm just trying to say that. So prime ideals come in 2 flavors. They're either split prime ideals like the ones I'm talking about right now, or they might be inert. So maybe it's just generated by a rational prime. That would be an inert prime ideal, or it might split, like the ones I'm talking about right now. So if you take a split prime ideal like this, like I'm saying, and then look at the spaces, you can compute these things in ways similar to modular symbols. This is another reason. This is one of the advantages of similarity in the geometry. For example, modular symbols, they don't work for Hilbert modular forms there, but they would work for Bianchi modular forms. So these spaces are trivial almost 90% of the time. So long time ago, I made explicit computations where you let your prime ideal run all the way with norm like 50,000, seeing like thousands of spaces. You compute, and there's nothing in it. So this is a stark difference than in the Hilbert modular forms case, or classical modular forms, or Hilbert modular forms. As your level grows, the space dimension will grow. So you will get bigger and bigger spaces. Whereas here, most of the time, it's just trivial spaces. You don't get anything. So it's a very different behavior. Right. Okay. So this harmonicity business, so very similar to the classical modular forms. From a classical modular form, you can cook up a holomorphic differential form, FCDZ, right, on your modular curve. We can do something similar here. If there is you can take this nice basis of differential one forms, maybe something like. So this is a three-dimensional manifold. So the differential one forms it's a three-dimensional space, and you can pick this, let's say, basis. And if your F is this Bianchi modular form, remember, so I'm landing in a three-dimensional vector space, so I have three coordinate functions. So this beta 1, beta 2, beta 3, they form a basis of differential one forms on hyperbolic 3 space. And if you just form the dot product, I guess if you look at this guy, then it's not hard to show that this is actually gamma invariant differential form. So it descends to a differential form on the quotient manifold. And actually, because F is harmonic, I guess it's kind of maybe built into the definition. So this guy, maybe I'll call it omega F, is a harmonic differential form on the quotient manifold. So this is the best you get. I mean, we don't have holomorphicity. We work with harmonicity in the setup, essentially. And we do get a nice harmonic differential form, which leads to notions of period. By integrating this harmonic guy over geodesic cycles, you get various numbers out of it. Actually, so this embedding here, this gives you an embedding of your complex finite dimensional vector space into the cohomology of the manifold, the RAM cohomology, if you want to see it that way. Yeah, F goes to omega F. You can also see this as, if you want, group cohomology, like this. But actually, you can, even using the same recipe, you can cook up a differential two form as well. There is a kind of a dual basis, because it's a three-dimensional manifold. There's a Hochstar duality going on between differential one forms and two forms, so you can actually get a nice basis for differential two forms and do the same trick, and get a nice harmonic differential two form and then that would give you an embedding into H2. So that's another difference with Hilbert modular forms. In the case of Hilbert modular forms, you get differential forms that live only in the middle degree cohomology. So if you have a nice differential weight to Hilbert modular form, you're going to live only in the middle degree cohomology of your Hilbert variety. Hilbert modular variety. Whereas Bianchi modular forms, they show themselves in both degree in other, not just the middle degree. Well, there's no middle actually here, three-dimensional, but they go in the two degrees together. So this embedding, actually, this is a generalization of what we call Shimura isomorphism. Modular forms, at least so-called cohomological type modular forms, manifesting themselves in cohomology through cooking up differential forms. So your weight 2 space of weight 2 modular forms embed, and actually there's a nice complementary space made out of Eisenstein series, which are associated to cusps. They together account for the whole cohomology. And in fact, this map, this isomorphism, is established by Harder in general for GL2 over general number fields, is Hecke equivariant. I guess I didn't talk about Hecke operators, but you can imagine that there's a very natural generalization of Hecke operators acting on this space of Bianchi modular forms and so-called Eisenstein series that I didn't define. Hecke algebra is a commutative, algebra of Hecke operators, and you can define these Hecke operators in a cohomological way on cohomology, and this map that F goes to its differential form is, or yeah, you can, yeah, I guess I didn't tell you how did I get to group cohomology. So it depends on how you look at things. As I said, the differential forms live on the de Rham cohomology, but then you can integrate those over closed geodesics, and that give you cocycles, as in the classical case. So you can land into this group cohomology, which would be just a homomorphism from gamma to C. So if you have a group element gamma, where does it go? Well, you take a random point in the hyperbolic free space and look at the geodesics, closed geodesic, gamma going to gamma, Q going to gamma Q, and you integrate your cuspidal differential form, omega F, over that closed geodesic, and that's going to give you, so this map is a group homomorphism, and that's your group cocycle. And so this is a isomorphism established by Harder in great generality for GL2 over number fields in automorphic representation language. Right, any questions?
Eisenstein 2 is a vector space, or is just one element?
This is a vector space. It's going to have dimension, will be essentially number of cusps minus 1. So it will, roughly speaking, you associate the Eisenstein series to a cusp. Right. So I guess perhaps a topic of interest, a fundamental topic that could be of interest to your group would be connections with elliptic curves, motives more generally. So here I won't be, of course, talking about. I'm really talking about abelian varieties here. So, as we know, in the classical case, there is a very famous relationship between elliptic curves and, well, isogenic classes of elliptic curves, and maybe I'll just write isogenic classes, and weight 2 rational new forms. Rational meaning that it's weight 2 is weight 2. New form makes it a eigenform under the action of all the Hecke operators, and rational means that the Hecke eigenvalues are all rational integers. And the connection goes as for each elliptic curve, you have this weight 2 modular form where the L functions agree. Or more precisely, these L functions have Euler factorization. So at all the places which don't divide the conductor of the elliptic curve, you have this nice point count, the kind of the arithmetic of the elliptic curve, which means local point counting over the finite field. So you reduce the elliptic curve modulo over, you reduce the coefficients of the elliptic curve modulo p. P is a nice prime, so that when you do that reduction, you still have an elliptic curve over the finite field, and you can count the points. There are finitely many possible points on that elliptic curve over that finite field sitting in projective plane. And that point counting will be essentially dictated by the eigenvalues of the modular form. So that's the relationship, right? The famous relationship. So, of course, it's very natural now to ask whether such a relationship exists for, in general, modular forms over number fields, in particular Bianchi modular forms. And so there are two conjectures in two directions. Let me start with the... So they were both actually completely open, and one was less open, and actually in the last maybe 10 years or so, there has been important breakthroughs, and so the following result is very recently announced. So all elliptic curves over imaginary quadratic K are modular. First remark is that, by the way, so if so, the notion of modularity is in the usual in the sense that I mentioned before. So that means that there is a Bianchi modular form, i.e., for all E over K, there is a Bianchi modular form. In fact, the level gamma naught of n, where n equals the conductor of the elliptic curve, the same recipe as in the classical situation, such that the L functions agree in the sense in the strong sense that I mentioned earlier, that point counting is for all prime ideals away from the level. The point counting on the elliptic curve is determined by the Hecke eigenvalues. The F has rational new form, means it's a Hecke eigenform with integer Hecke eigenvalues, is norm of the prime ideal plus 1 minus that integer Hecke eigenvalue of F at P. One little small remark here. I mean, it's really not that important, but if E has complex multiplication by the defining number field, by K, imaginary quadratic field, then the F that's corresponding to it will not be a cusp form. It will be an Eisenstein series. F is an Eisenstein series. That's a little special case that's already clear. But in general, this modularity. But yeah, so this is recently announced by James Newton and Anna Cariani and James Newton. very slightly earlier. Patrick Allen, Chandra Kare, and Jack Thorne proved modularity of elliptic curves or imagined quadratic fields of for density 1 elliptic curve. So modularity for density 1 set. And before that, maybe a year or two ago, there was potential modularity results. Meaning that you take an elliptic curve over K, you base change it to a bigger number field, and you guaranteed modularity there. But that's called potential. But this is over the base field K. So this is the last one. This is the, I guess, most general version. So this actually is quite a very significant result. This has been open for many years. I guess the crux of the whole potential breakthrough goes back to Caligari and Geraghty methods. Geraghty, butchering his last name. So they went beyond so it's the standard methods of Wiles, the so-called R equals T theorems. This is related to Galar deformation theory of Galar representations. They were quite they were kind of obstructed in the case of an imaginary quadratic field. Beyond the totally real fields, there was a kind of an ideological obstruction, and then this paper of Caligari and Geraghty came up with a novel way around how to go beyond totally real fields, and then a lot of big results, important papers kind of started coming out after that in the last 10 years. Right, but the converse direction, which is the converse direction is wide open, and it's even more actually complicated. Oh, it's almost time. The converse conjecture is, you want to say that this is the so-called analog of Shimura, Eichler-Shimura construction. Given a weight 2 modular form, given F weight 2 Bianchi modular form, is there an associated elliptic curve? Well, it turns out that you have to allow not just elliptic curves, but also so-called these false type of elliptic curves. In fact, one must expect, I mean, this is more rarely occurrences of so-called false elliptic curves. Not everyone likes this name, because this is an abelian surface I'm talking about, but we're calling it a false type of elliptic curve. So this is an i.e. This is an abelian surface A defined over my imaginary quadratic field, such that if you look at this endomorphism algebra, K endomorphism algebra, that's important. You take the ring of K endomorphisms, and let's tensor with Q so that you get this rational algebra. This endomorphism algebra is a division quaternion algebra. Or if you want to maybe see it geometrically, this is what people call a QM type, quaternionic multiplication type abelian surface. But you want to also ensure that all its geometric K-bar endomorphisms are defined already over K, are defined over K. As far as I know, the name false elliptic curve to such an abelian surface is coined by Serre in the 70s, I believe. So the point is that if P doesn't divide the conductor of this such an abelian surface, then A modulo P, if you look at this abelian surface over the residue field, this will be actually the square of an elliptic curve over that residue field. So modulo P at all the good primes, this abelian surface acts like the square of an elliptic curve. And that's why it's called, well, a lot of people call it false elliptic curves. And the conjecture then says that the conjecture is, I'll finish with this. This is wide open for every f in S2 gamma with rational new form. I guess I forgot to say rational here. Apologies. Of course, it has to be rational. Otherwise, you expect bigger dimensional abelian varieties. If f is rational new form, there is either an elliptic curve such that the L functions agree in this strong sense that I explained earlier, or there is a false elliptic curve such that the abelian, the L function of the elliptic curve, of course, it's a degree 4 L function, so abelian surface is a square of the L function of the modular form, so that the point counting over this abelian surface will be dictated by that the Hecke eigenvalue of the modular form, like this, for all p away from the conductor. I'll stop here. Thank you very much for your attention. And yeah, so I'll say that this is wide open, this conjecture, wide open.